Welcome, everybody. My name's Chris Stoltz. I'm your host today for this presentation on the vanadium batteries. I've got, first of all, a few little housekeeping tasks that we have to look at first. You are being recorded. If you don't want to be recorded, then perhaps you should leave, just in case you say something you don't want others to, or you don't want to be recorded for eternity. Leave your microphones, please, on mute unless you're asking a question later. But in terms of questions, I'll ask you to put questions in the chat and I'll go through them during the question and answer part of the presentation today. And then right at the end of it, if you can send your comments to Ingenieurs Australia Society at bigpond.com, and I'll remind you at the end of the session. So our first presenter today is Yifeng Li. Dr. Yifeng Li is a world-leading battery energy storage system and vanadium flow battery expert. He is currently leading the product development activity at VSUN Energy, a wholly owned subsidiary of ASX-listed company Australian Vanadium Limited. Before joining VSUN Energy, he worked for global energy company Voith Group in Germany, with a focus on the integration of VFB modules into large-scale systems, performance improvement and cost reduction of VFB, the standardisation of vanadium electrolyte. Dr. Li graduated from the University of New South Wales with a Bachelor of Engineering honours and a PhD in Chemical Engineering. His doctoral thesis project focused on process modelling, optimisation and control for VFB systems. During his PhD and postdoc fellowship, he worked at the University of New South Wales alongside the inventor of the VFB, Emeritus Professor Maria Skalalis-Kazakos, and process expert Professor Jai Bo. Ladies and gentlemen, please welcome Yifeng, and Yifeng, please deliver your presentation. And welcome to you too, I should say. My apologies.
Thank you. Yes, so I share my screen. Thank you, Chris, for the kind introduction. So do you see my screen?
Yes.
Okay, good. So thank you, everyone, and thank you for having me to give this presentation. And so we are trying to use this opportunity to give a broad education or an introduction of what is a vanadium flow battery and why is it a scalable and reliable solution for long duration energy storage. And so why do we need long duration energy storage? And here I am showing a Californian case study. And in California, there are 46 gigawatts of solar installed, but there is a little bit over 10 gigawatt of battery storage capacity. And most of these batteries, they focus, it's a short duration for 1 to 2 hours, lithium-based technology. And we can see that there is a significant gap when we're going into the nights, that significant energy that is still used based on fossil fuel. And there is certainly a need to extending the storage duration to shift the harness solar energy into batteries and deploy that during the night when the sun is not shining. And typically for long duration, we are talking about beyond 4 hours, typically 4 to 12 hours storage. And we can see that this long duration energy storage market is taking off. And so what is a vanadium flow battery? Or first of all, what is a flow battery? So the flow battery concept was first proposed by NASA in the 1970s. They initially looked at iron chromium chemistry, and iron chromium chemistry that's it is number one, it's very abundant elements, and it is relatively available. But there is a drawback for this chemistry, because you realize when you have iron and chromium on both on either side of the membrane, and you will realize that the crossover of a membrane would lead to a basically a cross mixing, and we refer that as a cross contamination. So over time, your electrolyte is essentially mixed. So then your capacity hence would deteriorate very quickly. And so, but nevertheless, NASA put a very important milestone and came up with a flow battery concept. A flow battery is basically made out of a very simple structure. So we have two tanks filled with electrolyte fluid, and we have cell stacks in the middle, which delivers the power. And because of this construction, the stack size, or mainly the active area, and the number of cells connected in series determines the power, and the tank size determines the capacity. So you can really design a system based on exactly what you need in terms of power and capacity, and you can size your system independently. And so this really sets a very important feature for flow battery. And so then why vanadium? So vanadium flow battery was actually, if we look at the vanadium, it's an element. It's sitting on the 23 place of the periodic table, and it appear naturally has multiple oxidation states, and in fact there are 4 oxidation states: vanadium 2, 3, 4, and 5. And each of the oxidation states will have a different color, and we have purple, green, blue, and yellow. And because vanadium is the only electroactive material, which in this case eliminates the issue of cross contamination through the membrane. But why NASA didn't look into vanadium? There are a couple of how would I say this? Conceptual misunderstanding back then. So later on, gets understood by Professor Maria Casacos. It was, if you look at the chemical reaction formula down here, it's so basically it says the negative side, it has it's converting vanadium 3 to vanadium 2 during charging, and it has a redox potential defined by thermodynamic. It's negative 0.26 volts in reference to the hydrogen reduction reaction. What that means, if you are going to charge, then the hydrogen ion will taking place and produce hydrogen gas. And until that reaction finishes, then you start your vanadium reaction. And this would be a problem, right? Because if you are deploying this vanadium solution in acidic solution or in neutral solution, there will be hydrogen ions available. And how do we ensure that the kinetic of the vanadium reaction is fast, and the hydrogen evolution reaction is sluggish? Then there are a lot of work have been done in the 1980s that's leading to a fundamental breakthrough. So, while NASA setting up an important milestone, a foundation, defining what is a flow battery and of the concept of flow battery. But the real breakthrough it comes into was in the early 80s. And the VFB was invented at the University of New South Wales by Professor Maria Skalas-Kasakus. And so the first patent of this technology was prioritized to 1984, which this year 2024 it's the 40th year anniversary, and which we just had the celebration with this invention, the technology invention 2 months ago, which there was an event held in UNSW and to celebrate this. So what Maria did back then was, as I mentioned, the flow battery is, if we look at the vanadium reaction, especially on the negative side, and she discovered that in order to prevent the hydrogen evolution, you need to have a large surface on the carbon electrode, and which means if you have you use large surface, let's say, for example, like a graphite felt instead of a graphite plate, which finely polished, and comparing to a graphite felt, which has a lot of these minor poles, and it's really facilitates the vanadium reaction, but inhibits the hydrogen reaction. So, and one of these fundamental breakthrough leads to the invention of this fantastic vanadium flow battery technology. And so why VFB is suitable for long duration, and number one, it is can be scaled with power to energy separately, as we discussed. And the larger the tanks, you have more duration, and the number of stacks or the active area in the stacks defines the power. And the lifespan of the battery can last 20 to 30 years with very little or even no degradation in performance. I can show you some data in the field that we can prove that. So the reason that there is no degradation is when you consider the electrolyte is essentially vanadium oxide that you dissolve in sulfuric acid. And the property of the electrolyte will not change because the property of sulfuric acid is very stable. It will not change. And that means the electrolyte that you use today, you can take it back and redeploy it to a second or separate installation. You will expect to have the same performance. And this technology is not flammable because it's 80% of the electrolyte it's water, and there is no flammable liquids or components in the system, and makes it one of the most safest and most reliable battery chemistry. And also because of there is no cross-contamination with vanadium, you can really do multiple daily cycles and with 100% depth of discharge without harming the battery. And the electrolyte, as I said, we can be recycled and reused indefinitely. And you can, if you decided the vanadium electrolyte that you want to dispose, and it is not really a waste, but you can also extract the vanadium and use it in the steel industry. And it is a proven technology, and there are a lot of deployments in Japan, China, in the US. And what I want to highlight is probably in China, there is a 100 megawatt and 4-hour battery installed in the city of Dalian, and it's in operation since 2022. And this is so far the largest flow battery installation worldwide. So here I'm going to show you an example of, for long-term performance, and it's a case study. And this is also a study that is published in the Journal of Energy Storage based on real data. And so in this case, it's a system manufactured by Enerox Cellcube, an Austrian flow battery manufacturer. And it's a 10 kilowatt, 100 kilowatt hour system. And it's relatively small, but this system was installed and commissioned in 2010, so it was 14 years ago. And as a demonstration project installed in Yifeng Energy Research Park, which as a research and development facility for renewable energy research. And the battery is connected with renewable generations and solar panels and wind turbines and also local loads to form a microgrid setup. So what we want to highlight is this system, since it was commissioned in 2010, it has been in operation continuously with very little downtime, and the performance. So I have analyzed this system since the beginning of the operation, and the electrolytes, it is very stable over. So I think the last data point that I obtained from this system was in 2023, and over 12 years of continuous operation, the electrolyte has been very stable, and there is very little degradation. And the overall system efficiency is also very stable, as you can see on the table here. There is almost no change in the overall energy and the overall system efficiency. And the study, what is also very interesting is we, in one of the battery stack, we actually detect some aging effect, and we can see on the right-hand figure here. And this is, we conducted so-called an impedance spectroscopy analysis. And the idea is to try to understand what are the components causing the internal resistance inside a battery stack. And we found out that there in one of the stack in particular, there is some aging effect leading to an increase in the internal resistance. But then we also, in the study, we suggested to perform a treatment which, by reversing the polarity, because the chemistry is very symmetric, right? So on both sides, it's a vanadium reaction, and you don't have any other contaminants or any other cross-contamination effect. So you can really reverse the polarity electrically and also hydraulically. And we found that comparing the impedance results before and after doing this reverse polarity, we see a dramatic difference in terms of stack resistance. And we see that the stack resistance can be largely recovered, or almost 100% recovered, by performing this reverse polarity. And this suggests that this can recover the stack degradation if there is any. And on top of the figure, it shows the capacity of the system. It's remained very stable over 12, 13 years. And so if we look at that, the energy efficiency or the system efficiency is relatively low, but don't forget this is like a technology that's 12 years ago or 14 years ago. And what is the latest development then? The battery stack performance comparison. And so I had the chance to evaluate almost all flow battery products in the world and compare the performance. So in this particular case, and this presentation I also presented in the International Flow Battery Forum in 2023. And so in this study, we basically evaluated stacks from 4 different manufacturers, and we named that as A, B, C, and D. And it shows that the stack efficiency has been significantly improved over past decades compared in the previous study, which has around 70% on the system efficiency. And compared here, if we look at the during nominal power cycle experiments, some of the stacks most of the stacks can reach over 80% round trip efficiency, and some of these even reach 88% at 2/3 of the rated power. With the rated power is defined to be a maximum continuous discharging power in between the maximum and minimum state of charge. And also we can see that the per stack power density has also dramatically increased. And we can see that some of the stacks can achieve above 170 milliamp per square centimeters per cell as a power density, while in the past was significantly lower. And so in VSUN, we also have several customer projects. One is Ingenieurs Limited, which we installed in Nova Nickel operation. And another one is by Horizon Power, and it's installed in Kununurra. And the Horizon Power battery is manufactured by Invinity. It's a Canadian flow battery manufacturer. And in this battery, there is a small some portion of the electrolytes also manufactured here in Australia at our electrolyte facility based here in Perth. And currently, we are also working closely with Horizon Power to evaluate the performance of this battery, in particular under this climate in Kununurra. It's a very humid and tropical weather, and we are very interested to see how this battery performs under this climate condition. And further, we also recently launched our Project Lumina with the focus to utility scale. And the idea of Project Lumina is we would like to design a so-called deconstructed system aiming to for the utility scale space, and with the ability to extend storage duration but minimize any modification required. So essentially adding more storage tanks to the an existing system in order to extend duration. And so this Project Lumina is we are aiming to develop as a solution for aiming for the 100 megawatts and 4-hour system initially, but we are looking into extending it into 8 hours and or even 12 hours when the needs appear. So In conclusion, VFB is established technology invented in Australia in 1984, and the technology has proven performance track records and has shown in multiple studies. And the latest development shows the technology of the battery has achieved an efficiency as high as 88%. And with these, combining a good performing stack and a good battery management system, we see that it is possible to reach 80% round trip efficiency on the AC/AC level, which close to the performance of a lithium battery, lithium-ion battery. And VFB plays a very important role in the long duration energy storage space and to support the energy transition. So thank you for your attention.
Thank you very much, Yifeng. And I just remind everybody that we'll have some questions at the end. And if you can please put your questions in the chat and we'll go through them after our next presenter. Speaking of which, our next presenter is Zamien Sumich, and Zamien has 20 years of experience in renewable energy with extensive background in large-scale solar installations. He joined VSUN Energy in 2019 and is one of the country's experts in vanadium flow battery technology and its unique advantages for long-duration energy storage. VSUN Energy was launched by AVL in 2016 to grow the VFB market in Australia and utilises batteries from a range of manufacturers for its projects. The company is a fully owned subsidiary of ASX-listed Australian Vanadium Limited, which is developing the Australian Vanadium project in WA and has an operating vanadium electrolyte manufacturing facility. Together, the companies are leveraging the full pit-to-battery supply chain in Australia. Ladies and gentlemen, please welcome Zamien Sumich. And Zamien, are you able to share your screen?
I certainly will.
Very good. There we go.
Okay.
Yeah, you might want to flick that to presentation or whatever it's called. Because we're seeing the what do they call them? The fingernails down the side.
Is it in, I don't use Zoom very often, so is it in that or is it?
No, you should just press on, in the bottom right-hand corner, there's a little picture of a screen next to that slide. Isn't it? It's one of those.
That one.
There we go. Okay, so yeah, thanks for.
Difference.
Is that okay?
No, it hasn't made any difference on my screen, but if other people can see it.
You'll have to do it.
Me?
No. Sorry, Zamien will have to do it.
Yeah, that's right.
Yeah.
Yep. Oh, up the top there, actually. And the top left. Isn't that from?
Yeah, very top left there.
Press that. No.
If Zamien can do that with his cursor.
Yeah, I don't know.
Good to see. I'm good at driving.
Yeah.
1 second. All right. Well, maybe I'll just skip through if we can. We can see it anyway. So
that's right.
I need to do some rehearsal on my presentation skills, right? So yeah, look, really appreciate the time. I'll skip through this reasonably quickly because I'm assuming there's going to be a few questions towards the end. Just to provide a little bit of clarity on what our motivation, what our drivers are as a company. So we've got a parent company that owns a primary vanadium deposit located just south of Meekatharra in Western Australia. To give you a bit of a quantum of the amount of vanadium that we have there, we've got around 1.1 to 1.2 gigawatt hours equivalent of vanadium pentoxide at that mine that we can produce over a 50-year period currently. There's more of an asset there, but you know, the benefit of drilling out past 50 years isn't necessarily there. The structure of the business is that we, or that the project is that we have a deposit just south of Meekatharra, as I mentioned. We're planning a processing plant which will be located closer to the port of Geraldton, near a town called Mullawa. where we will produce a higher purity vanadium pentoxide. Now, that product from there is a battery-ready product. So that vanadium pentoxide can either be sold into the steel market, where the primary demand for vanadium has been over the past, well, however many decades that it's been in use. But the biggest growth space is in energy storage. And as Yifeng mentioned earlier, in particular in China, where there's an operational 400 megawatt hour VFB that's been in operation for over 2 years, but where there are multiple gigawatt hour scale solutions now being built, and where there is a significant gigawatt hour scale, many multiple gigawatt hour scale manufacturing facilities being constructed. The main reason behind China's focus on vanadium flow batteries is really around two things: diversification outside of a lithium energy storage market. Obviously, the longevity of the product is obviously beneficial. Their shift to longer duration applications, but also the fact that they control and produce 60% of the world's vanadium. As you can see in our structure, we're producing a battery-ready product. Unlike many other technologies where there's further refining required, we don't have that. And it's the same in China. They've got battery-ready vanadium in vast quantities that requires minimal further work to be able to get it to a point where it can go into a battery. So from the processing plant in near Mullawa, we then will have vanadium pentoxide go to an electrolyte plant in Perth that's currently in operation. We'll also build electrolyte manufacturing plants on the East Coast, depending on or will be located depending on where the major points of demand are. So we foresee that we'd have facilities in places like, in particular in Melbourne, in Victoria, New South Wales, potentially in Queensland and South Australia. And that's really driven by the fact that you can reduce costs on project deployment by manufacturing that electrolyte close to the point of demand. In terms of the content of vanadium in a VFB, it's significant in comparison when you look at lithium in a lithium-ion battery. Again, motivation from our side, we've got a parent company developing a primary vanadium mine. There's a significant quantum of vanadium in a vanadium battery. Hence, the value for us is that if we can get as much of that product out of the mine and into a battery as we possibly can, it adds and increases value to us as a business. Excuse me. In terms of what we're currently in the process of doing, Yifeng mentioned earlier Project Lumina, which we're working on in the utility space. We're working with a number of EPCM contractors to assist us in the development of that product, which we're looking to deploy in the next 2 to 3 years. We've got relationships with existing proven OEMs, as well as some of the more novel or newer OEMs in the market. We have not quite, I would call, agreements as yet, but arrangements with some funding entities who are willing to back the product as a 30 to 40 year asset. And we're specifically talking here infrastructure investment firms. So the types of firms that are used to investing in products that have a much longer lifespan than what you would traditionally see with energy storage in terms of lithium ion. Energy offtake, we're working on developing relationships with the likes of gentailers, government entities, both on the East Coast and West Coast, for utility offtake through the use of these VFBs, these large-scale VFBs, and then in discussions with land access, so project developers, gentailers, government entities, as I mentioned, large commercial and industrial players for land access for these solutions. In terms of the company structure, again, we've got an upstream portion, which again is the mining and processing for our parent company, Australian Vanadium Limited, which is, I'm not sure if I mentioned, but an ASX listed company. The electrolyte manufacture, which we're already conducting here in Western Australia, but will expand throughout the country. And then the downstream portion, which is VSUN Energy, which will be we've developed small scale solutions, but we're now focused on the delivery of utility scale VFB solutions. Yifeng mentioned earlier around the need for long duration. Look, we've done some LCOS analysis that, the 4-hour type solution for a VFB is competitive with lithium, which I'll share a little bit of info on soon. But the big market for us longer term is, looking at the need for long duration storage, and that then starts to exceed 8, 10, 12, 14, potentially into intraday duration of storage. And when you look at regions like Victoria, where there are significant, or there will be in particular, significant shortfalls coming up with the impending closure of coal-fired power stations, there is a need for multiple technologies, and this is something we emphasise as a business. The vanadium flow battery is not a silver bullet. It is not the answer to all of our requirements for long duration storage. It is a part of the solution. And when you consider that we've got a mine that can produce just over a gigawatt hour per year for 50 years, that's still not going to be anywhere near enough for what is needed for this country to be able to decarbonise our grid. So we will need other flow battery technologies to become commercialised. There aren't any that are commercialised to the level that a vanadium flow battery is. They're many years away from getting there, but we will need them to become successful. We'll need pumped hydro. We'll need multiple other technologies to be able to come to the party to support that transition. As Yifeng mentioned, I won't sort of focus on this too much, but it is something we've been working on for quite some time, but we've now invested significant resources and capital internally as a business to develop a utility scale solution. It's not something that's unique to VSUN Energy. Yes, we have access to high purity vanadium product. We've got access to supply chains and manufacturing capacity and technical expertise. But really what we're doing is looking at what's happened in China, what's happening in China, what the need is in Australia, and we're really just duplicating what they're doing. These facilities have been built in places like in Japan and in particular in China, which I'll keep referencing, but it is not a new technology. It is commercialised, it is proven, it has been deployed at scale for many years. So we're just tweaking it to accommodate for Australian conditions, to accommodate for the Australian market. And as was mentioned previously, the current Australian market incentivises a 4-hour duration solution. That's what you can monetize. For us, we're designing this solution so that when it does get deployed, whether it's in 1 year, 5 years or 10 years after deployment, it is easily expandable to 6-hour, 8-hour, 12-hour plus duration by simply adding tanks on. In terms of the LCOS that I mentioned earlier, if anyone wants to look at this in a little bit more detail, we had an announcement a couple of weeks ago around an analysis that we've done internally and has been verified by an independent body. The LCOS analysis that we've done on a 4-hour VFB in comparison to lithium, and again, it should not necessarily be a competition between the two technologies. We need multiple technologies, but lithium is what everyone knows and uses now at scale, but it is competitive at 4-hour duration. It gets even more so at 8 hours and will be even more so as the duration extends. And that is because as we extend the duration, there is no additional augmentation costs. There is just the additional cost of tanking and electrolyte. So for us, Project Lumina is driving home the emphasis on the fact that the LCOS in comparison to lithium, particularly over long-term asset life, is very, very competitive. I think one of the biggest hurdles for us at the moment is the race to be second. No one wants to be first in Australia. Doesn't matter if it's been done 1 million times overseas. If it hasn't been done in Australia, it hasn't been done anywhere. Moving on to, I suppose, the electrolyte plant. We haven't sort of touched on that too much, but it has been operational for this year in WA. You can see it in the background of that image there. That's on the left-hand side is our CEO, Graham Arvidson. On the right-hand side is our Premier, Roger Cook in Western Australia, who visited recently. That's an electrolyte manufacturing facility that produces 33 megawatt hours per year. As you can see, it is not overly complex. When I said that we would build these facilities on the East Coast or in areas of demand, it is not difficult for us to do so. We're not talking mass manufacturing facilities with automation and huge quantities of capital sunk. It is all about tanking. There are some other requirements in terms of manufacturing, but really it's a mixing of vanadium oxides, water, sulfuric acid, and then away you go. So it's a simple process. We've done it. We're in the process of getting verification from multiple different OEMs. And as Yifeng mentioned, we have electrolyte in a VFB currently on operation in QnA for our remote energy utility in Western Australia, Horizon Power. And I suppose just on the last point, some of the stuff that we're looking at in terms of deployment and deployment sites, in particular brownfield sites, commercial industrial areas. But, you know, look, one of the big benefits of the technology is the fact that you can build it in areas that you probably would avoid with lithium ion, in particular, you know, around the risk of thermal runaway. We're able to build up into, you know, residential areas, commercial industrial areas where, you know, otherwise you would probably avoid with the risk of thermal runaway events. For us, that's not an issue. In terms of space and footprint, there is a larger footprint requirement for VFBs at small scale. Counter to that, at large scale, it actually takes up a smaller footprint because we do not need to segregate containers to prevent thermal runaway cascading down as you do in lithium ion projects. So for us, as we get to larger scale, and that's when we get into the tens, into the hundreds of megawatt hours, we can build vertically and therefore take up a much smaller footprint to that of lithium ion projects. I think I'll stop there, and I'm assuming we'll have some questions and Q&As.
Very good, Damien. Thanks very much for that. We went at a good pace. Well done. So now what we'll do is we'll go through some questions, and you'll see the questions in the chat, and I'll start at the top and